So the first question that we'll ask is, we already have known about, you have learned quite a bit of analytical computing, right? So what is the difference between analytical and, should I say, instead of scientific, should I say numerical computing? Because analytical computing is also scientific computing only, and that you have learned so far. So what is the difference between analytical and numerical computing? So analytical versus numerical. And it's not really a war. When you say versus, it looks like a war, but it's not really a war. They're complementary. So one works at certain places better than the other. So you have to learn both if you want to do something important in physics. And analytical computation. So how many of you think that the numerical computation is a recent phenomena that like it was developed in last 50 years? Have any idea when the numerical computation was developed or was started to develop? Anybody?
Sir, by Alan Turing.
Alan Turing, which is like 70, 80 years ago.
Yes, sir.
Anybody else?
With the invention of logarithms, possibly.
With the invention of logarithms, which was quite a lot of bit ago. Anybody else? So there are different things that we learn, right? So one of the things that we learn is called a Newton-Raphson method for solving for the roots of a algebraic equation. And you can immediately realize that it was invented by Newton. Numerical computation is as old as analytical computation. When people realize that there are certain problems which cannot be solved using closed form analytical techniques, they started to develop the numerical techniques then itself. So it's almost developed at the same time as analytical computation.
So
yes.
So taking square roots, cube roots, all that also includes numerical computation, right?
Those are done by the binomial theorem. What is called the generalized binomial theorem is one of the thing that Newton did in good old, like 450 years back. So you may ask the question that, so you call it numerical computations, but there was no computer at that times. But if you do a little bit of study of literature, not literature, study of linguistics, you know that you use ER like computer at the end of people who used to do that job. Like, for example, farmer. So who used to farm? So there are human computers at that time. So all these people actually will work out all the numerical numbers by hand without even a calculator or even a mechanical calculator, and find out the values. And that's quite a painstaking task. We used to take a lot of time, but people used to do that way. Okay. So it's a very old subject. Now, to start with, what we will do is, let's start a review of what we do in analytical calculations. Okay. And we have learned so many analytical techniques, obviously, that cannot be covered in a 2 minutes wrap up of that. So let's take an example. So say, one class of examples that we do in analytical calculations is try to figure out the trajectory of a particle, right? And what have you learned? So you have obviously learned Newton's methods, but then you have also learned Lagrange methods and Hamilton's methods for solving for the trajectories. Now there, you start with your Lagrangian and then write down the Lagrangian, find the Euler-Lagrange equation, which is a differential equation, right? Second order differential equation. So this is I'm writing as an example because obviously, if you are solving a different problem, for example, the electric fields because of charges and currents, there you have to solve not an ordinary differential equation, but a set of partial differential equations, which are called the Maxwell's equations. But in this example, we solve an ordinary differential equation, right? And then we use analytical techniques to solve this second order equation. And in the way, we may need to do certain approximations.
Excuse me, sir.
Yeah.
Sir, in Euler-Lagrange, we take partial derivative with respect to the generalized coordinates, right?
That's all right. But the equation that you get after doing that, the Euler-Lagrange equation, the equation that you get after that is a second order differential equation, ODE, right? I'm not saying Euler-Lagrange equation is a second order ODE, but what you get out of it is a second order ODE. It's essentially Newton's laws of that, right? And then you try to solve that, and once you try to solve that, you get an algebraic expression for the variables. Right? So you get an algebraic expressions for the variables. Until this point, there is absolutely no use of any numbers. So these all done with symbols. So sometimes we like the Roman symbols, sometimes we like the Greek symbols. But these all are done with symbols. After that, what do? Now you put in two things. One is the initial conditions. What is the other thing that you need? You need the dimensions of the system, right? So this is what you do. For this, you also choose a unit system like CGS or SI, whatever is your choice, but you have to choose a unit to write down the dimensions and the initial conditions. Again, if you take a concrete example, the second order ODE, maybe we are solving the pendulum problem again, which is the easiest problem and the only problem I can solve. So this is the pendulum equation, differential equation. So then we said that we use an approximation. So that's an analytical approximation. So you say that we will only work for the cases where theta is small, so sine theta is theta. So you write down the equation this way. Then you get an algebraic expression for the variables. The variable here is theta itself. The solution is theta as a function of t, which is theta 0 cosine of and next you use initial conditions. So you say that theta at t equals to 0 is, say, 1 degree. It has to be small with this approximation. You cannot use theta equals to 10 degree here. So then this solution doesn't work. And so say psi equals to 0. So that gives actually psi equals to 0. And then what else do you need? You need the dimensions of the system, which means you have to tell what is the value of L. So say I call it 1 meter. and g is something that also you have to measure, and then say that is 10 meter per second square. Okay. Now, once you have used up all these, now I have theta as a function of t. I have run out of space here. Let me write it here. So I have an algebraic expression now, which is theta as a function of t, which is 1 degree, then cosine of root over of 10t. And any value I choose for t where I want to calculate theta, I can calculate it at any theta, any time. Okay, this point is very important. So let me write it here. So calculated at any time. Okay. So what do I mean by calculated at any time? I mean that, say I want to calculate at t equals to say 10 days, I can still do it. I can still calculate what is the value of theta as a function of t after 10 days without calculating what is the value of the function of t at the end of the first day, second day, third day, fourth day, etc. I can directly calculate what is the value of the function of theta at the end of 10 days. So what we have done so far is that we have gone through a particular way of calculating things in physics, and this is the analytical way of calculating things in physics. You have done it many times and you have had quite a bit of training on it. Everybody is absolutely familiar with how to do analytical calculations, but there is no harm in seeing it again and emphasizing few of the facts, few of the steps that we take during the analytical calculations. If you have any question at this point, then ask. Otherwise, we'll proceed. So this is all right. So let me change the page.
Yes, sir.
So let's come to numerical now. So how do I do the same problem numerically? And what is the advantages and disadvantages of that? The numerical technique doesn't start from Euler-Lagrange equation most of the time. It starts from the second order differential equation. You start with this equation. So I've gone to the next page. So it starts with this equation.
Excuse me, sir.
Yeah, go ahead.
So is it just me, sir? We are just saying the first, like in the presentation that you're doing in the meet. Can anyone else confirm?
Yes, sir. It's only the first page is visible on the presentation.
Yeah, right.
See it on second page of Jamboard.
I have changed it there also. All right. But see, easier for you is all of you can open the Google Jamboard individually, because so then it first gets updated in the Jamboard and then gets updated in the presentation. So it will be out of sync with what I'm speaking, right? So if all of you open the Jamboard individually, I have kept it just for my reference only. But if you look at the Jamboard, it will be easier for you. Okay. But anyway, thank you. So because I had to change myself also. Now, an usual approach to solve this will be not to solve it directly a second order differential equation, but break it into two first order equations, which is like saying not to solve it in the Lagrange way, but to solve it in the Hamilton's way, where you always have only first order equations. So I will break it into the first order. And why all these are done? So that we will learn over the course. This is just can take as an example for the time being. and some of the things we'll discuss today and some will come during the course. Okay, so let's break it into the first order. So what will I do is that, so I not always need to write down in terms of momentum and position. I can just say that I define d theta dt as y, and then dy dt is minus g by L sin theta. That will do, right? So that is the same, these two equations gives you the solution to the same problem. Like G looks very odd. Okay, did I use small l? I used capital L. Okay, now at this step itself, the next step itself, while you are solving it in computer, and all of these has risen, which you will learn as we go along in the computational physics course, we need to know the dimensions of the system. So you use the dimensions of the system. Let's write system dimensions. To cast our equations with dimensionless variable. Why is this important? Again, we'll learn. So what will I do? So in these two equations, what is the dimensions that you have? What is the dimension of theta? See, I guess that you remember the dimensions, which is only m, l, and t, right? Only 3 dimensions, because these are the only things that we can measure. Okay, so what is the dimension of theta?
Radian.
0.
Radian. So what type of dimension is radian in terms of m, l, and t?
It's
Dimensionless.
Dimensionless.
Theta is dimensionless, so theta dimensionless. What is there in this equation which has dimension?
G
has
and
dimension.
L.
E has dimension. G and L also has dimension. So I need to look at the dimensions of the system to figure out a dimension of time in the system. And can you tell me a dimension of time in this system? It's obvious because you know what the system is.
Under root L by G.
Right. So I have a time dimension. So I choose a time dimension. So this is my choice. And this is coming from the dimensions of the system. So this is root L by G. This has a time dimension. So what do? I recast my time variable. I write it in terms of tau times some capital T. So capital T is my new variable. What is the dimension of the variable capital T?
1 by T.
So dimensionless.
It's dimensionless, right? But T, small t in the left hand side has dimension of time. Tau has a dimension of time, so capital T is now dimensionless. So I got 2 dimensionless variables, but I have one more, which is y. And this I can write as y, capital Y by capital T. Remember, small y has 1 by capital T dimension, so now capital Y is also dimensionless. All right. So now in terms of these variables, let us try to write down the equations. What will happen to the first equation? So d theta, I will do the first equation explicitly and then I will write down the second equation which will verify, because first is easier to do. So dt, I will write tau is a number, so this is just d capital T, and y small y is capital Y by capital T. So this equation becomes d theta dt equals y. Can you tell me what the other equation will become? dy d capital T, what will this be?
Minus sin theta upon tau square.
Is it?
I think maybe.
Anybody else? Any dimension, right? So if you have tau square left, then
Yes,
that
sir.
equation is,
It's
Yeah.
minus sin theta by tau square.
see, what will happen to dy? D small y will get 1 by tau, right? 1 by tau, yes. And dt also will get 1 by tau. So this will be tau square, which was in the denominator in the left hand side, I have brought it here, into g by L sin theta, right? What is tau square times g by L?
1.
So this is just minus sin theta. Now you look at the beauty of the equations. There is nothing which has any dimension. Right? So this is the second step that we do. See, what is d theta is already dimensionless. We did not change it, right? And in the denominator we had d small t, and small t is tau, which is a constant, times capital T, which is written here. So d small t is tau times d capital T, which I have written. And in the right hand side I had small y, which I have written as capital Y by capital T. All right. So now, sorry, yeah, you are. I think that is what you are trying to figure out, point out. So these are not capital T. This should be tau. Fine. I'm sorry. So y times tau is capital. Sorry, y small y times tau is capital Y. Is this all right, or should I?
Sir, what is capital T? I don't understand.
Okay. So what is tau? Tau has some dimension of time, right?
Yes.
Tau
Sir.
has some dimension of time. Now I am writing my time t variable as tau times capital T. So that capital T is nothing but a dimensionless time, right?
Okay.
So it is
Now
a constant, sir.
its capital tau is a constant, right? So this is given the dimension of the system, which is capital L. Capital tau is a constant. Capital L is 1 meter, so then it's constant, right? Capital tau is essentially, in our example, 1 by root 10.
So then what does differentiating with the constant mean?
1 second, one at a time.
सर हम लोग
Yes.
इस इक्वेशन को डायमेंशनलेस बनाना क्यों चाह रहे हैं, मतलब व्हाट इज द रीजन बिहाइंड दैट?
That I said that we will understand that. See, so then you have to. I cannot teach you the entire computational physics in one day, right? So we'll understand that as we go along, why we want to make it dimensionless. But for the time being, we need to do this step here. The point that I'm trying to making is that in the analytical way, in the last step, you used the dimensions of the system. Here we are using almost in the first step or the second step.
Sir,
Okay. So if I do not know the
sir,
dimension
how
of the
this
system,
capital Y is dimensionless?
if I do not have the dimensions of the system already known to us, my numerical methods mostly will not work. Okay. Why capital Y is dimensionless? What is the dimension of small y? 1 by time, right?
Yes, sir.
So capital Y is written as, so capital Y is small y times tau. Y has a 1 by time dimension, tau has a time dimension. So capital Y cannot have any dimension, right? Okay, so let's proceed. Let's see what good it gives us. And that will be kind of apparent in the next step. So now, what we have to do, the next step, is to evolve, literally evolve the equations or evolve the variables in time, starting from initial conditions. What do I mean? So again, if you look at, as compared to the analytical technique, we are still using the differential equation. And after solving the differential equation, getting an algebraic expression like theta as a function of t, then we used this initial conditions to solve for theta at any t. Here, we said that we'll, at this step only, with the differential equations only, we'll evolve the variables in time starting from the initial conditions. I need the initial condition at this stage itself. Okay, so now here comes, and till now we do not have any approximation. You see, I have not approximated sine theta to theta. I don't need that. If I wish to, I can do, but I don't need that approximation. In the analytical case, if you do not do, then you cannot solve for the algebraic expression. Now, if you remember, when I say d theta dt by definition is limit delta t tends to 0, theta as a function of capital T plus delta t minus theta as delta t, minus theta at t by delta t. So this delta t tends to 0 here. Okay. Here I make a numerical approximations. Numerical means that I make an approximation which is required for numerical calculations. What is the numerical approximation? The numerical approximation is delta t is not tends to 0, but it's much less than 1. Okay. Now, remember that whenever I say that something is much less than something, these two something should have the same dimension. So here I can say delta t is much less than 1 because delta t doesn't have any dimension. So delta t is a dimensionless quantity, which I say is much less than 1, that makes sense. If I say that I have t, which is time here, much less than 1, it doesn't make any sense. 1 in which unit, you should ask. 1 day or 1 second or 1 millisecond, 1 year, etc. Here it makes absolute sense, and that tells you that why I need to do that, need to change it to dimensionless quantities. That's partly the reason. So once I do this, then, so this is the definition. Now I do the numerical approximation, which is d theta dt is approximately theta as t plus delta t. This delta t is a small value, which you have to choose now what is a small value. But this. And then this is equals to y. So theta at t plus delta t is theta at t plus capital Y at t times delta t. So this comes directly, just changing this delta t, I multiply with yt and then bring that theta of delta t in the right hand side. Okay. Similarly, if you just work out, so y as a function of t plus delta t, this will become y as a function of t minus sine theta. Now this theta, so let me, for you to remember, so this theta is evaluated at t, what was the value of theta at t into delta t. Okay. There is approximation, remember, there is approximation going on here. It's not an exact differential, but then you can still do it if you are doing it this way. Now what happens? I can use this equation to get what is the value of, so to start, I start with the value of theta and y at t equals to 0. So that's my initial condition. So you start with theta at t equals to 0, y at t equals to 0. Once you use this, once you choose a delta t, choose delta t. So remember that it has to be much less than 1. So say, let's say that you have chosen is 0.001. So what do I get? I get theta and y, theta and capital Y at, so I should write here as capital T equals to 0, right? So I get theta at capital T equals to 0.001, y at capital T equals to 0.001. What do I do then? I repeat. Now repeat. To the time capital T at which you want to learn, you want to know theta. So you get the point. In the analytical case, if I go back, in the analytical case, I can calculate at any time once I get this expression. I don't need to calculate at the intermediate times. Here I don't have any such way. I have to evolve the system to the time capital T at small steps. One at a time, I get all the values in between, and then finally I get the value at the value of capital T. So T may be 1 day. Okay, so that's a big difference between the analytical and the numerical computations. So we have just gone through an example, and we saw that the way the computation works is quite different in the two cases, though they start from the same differential equation. And here I really don't need to write down sine theta as theta. But if you wish to, if you say that, okay, I'm working with small theta, so I will just use sine theta as theta, I know that the analytical case is correct. So that you can do, but it's not required. Now there is an approximation going on, as we said, which we have already discussed, which is coming because the differentiation is done with assuming that delta t equals very small value, very much less than 1 will suffice.
The trade-off here is we don't approximate sine theta, but we have to do a lot of recursive calculations, right?
You have to do a lot of right. You have to keep changing a lot of values. But you see, say you want to solve for sine theta, your theta at t equals to 0 is not 1 degree but 10 degrees. Okay, you can have a problem like that, right? How will you solve it now? You don't have any other way other than using this method now. Because your analytical method doesn't work, you already know. Right? So there is a trade-off, and that's what we will discuss next. That it's not that numerical methods is superior than analytical method or analytical method is superior than numerical method. As I said, that both has to be used hand in hand. And if you use them cleverly, then you will get the most appropriate result. You will never get the exact result. Okay, so any questions we'll take and then we'll address what are the problems in numerical computation and what are the sources of those problems. So any point you have any problem in understanding, and if I am going too fast or too slow or whatever, so you should immediately tell that. Okay, so then we can correct our actions and we will learn more. So if you just keep quiet, then obviously.
Hello,
Yeah, go ahead.
sir. Capital T and capital Y is dimensionless variable are constant,
Capital Y is not constant, right?
and capital T.
Capital T is also not constant. See,
Okay.
small t is not constant, it's a variable. Small y is also a variable, right? Now, the unfortunate thing is that they have dimensions. And so what we did is that we used a physical dimension of a system, in this case capital L, which gave us a time scale tau. 2 pi of this tau is nothing but your time period, which you know. But obviously for sine theta, that may not be the case. So tau is a dimension, full time dimension thing, number. So what I did is that I divided t by tau such that I get a time variable which doesn't have any dimension. Or you can say that capital T is in units of tau. The unit of capital T is tau. Tau is 1 second, then capital T is given in 1 second, in seconds. And where it was useful? So one place you have already seen it is useful is doing this approximation. I don't need to say that with respect to or in which unit capital T is small. The unit is coming from the system itself. All right, so let us now switch topics, or I mean, it's a part of what we have been discussing. Yeah, go ahead.
So, what conclusion we get from this final result? What is
we just have looked at the difference between analytical and numerical computation with a very specific example. Okay, we understood that neither is superior, but they have this, they solve the same problem, but two completely different ways. In one case, you get an algebraic expression, and then you use the dimension of the system and initial conditions to get to an expression for your variable, which is a function of time. A single function, it's a function of time only. And then I can put the value of the time. If 5 days, I get the value of theta. As extra steps like changing it to dimensionless variables, etc. And then there are extra approximations where you don't do proper differentiations but do an approximate differentiation. But what you do is you use the dimensions of the system and the initial conditions at the first step or at initially, and then you evolve the system. You really evolve the system means that you calculate what is happening to the system at each and every time step up to the time step you want. Obviously, you will not calculate up to the age of the universe, but you will calculate up to, so if you want up to 5 days, you calculate it up to 5 days. But you cannot just put the value of 5 day in your some equation, and then one computation will give you the value at the 5 days, which the analytical does. Okay, so there are these differences between these. Yes.
Sir, 5 days, we have to keep incrementing by small steps, right?
Right. You have to keep incrementing by small steps. And how small it is depends on the dimension of the system, depends on L. If L is very large, then the increment has to be large. But once you are looking at in dimensionless units, it's already in the units of the root over of L by G. So this, if I choose to 0.001, then I will be happy. I don't care about actually it is 5 days or 5 hours.
So, but 5 days will take more time, right?
It will take more time. That's why nowadays we don't we do it more often with numerical computation, because our computers are really good at repeating steps, and it takes almost no time to evolve this to 5 days. If you want to use it by hand, which the old people used to do, it may evolving to 5 days may take 50 days of your time. Nowadays, it will take 5 nanoseconds or 5 milliseconds.
Oh, okay. Yes, sir.
Okay. So I give you a homework here. Okay. So evolve the system to, don't really evolve, to 5 days. Okay. One step takes one of these steps. So this is one step, right? One of the evolution. So say this takes 1 second. In one case, you take 1 second, and another case, you take 1 millisecond. Okay. And then, so this is one case. The other case is the value of L is 1 meter, 1 kilometer, and 1 millimeter. So you get six combinations. So value of L is 1 meter, and one step takes 1 second. Evolve the system to 5 days. So you have to figure out how much computation time it will take for these 6 combinations. Okay. If you have understood what we discussed, then this is a straightforward problem.
Sir, can we take any initial value?
It really doesn't depend on that.
Oh, okay, sir.
Okay, so I will not tell you. So whatever the parameters given here, so like I have given delta t equals to 0.001, etc. So whatever the parameters given here, g you can take as 10 meter per second square. You have to figure this out. Okay, so I think we'll not go to the next discussion. It will take some time, so we'll do it in the next class.
So with
But
computation time, do you mean like we have to give in the form of O of?
So you have to give in terms of seconds. See, one step take 1 second. So you have to figure out how many steps, multiply that by 1 second, total computation time.
Okay, sir.
Okay, so I will not go any further today because that will probably, I mean, if we start, we will not be able to finish the discussion in 5 minutes. But that's all right. We'll do it next class. So we have plenty of time for questions now. So you have the Jamboard ready for you. I mean, it will be there in this thing. And I thought that I will record the lecture video, which I forgot. But from next day, please remind me at the beginning that if I can, I record the lecture. So that I will also try to keep. But please come to the lecture. Oh, very good. So where can you give me the link so then I can keep the link in the. So that will be good. So any other questions? Tell me honestly that any of you think that I am going too fast. If you think, you should tell, because the class is for you, not for me. Or the other way around. So if you think that I am going too slow.
It's fine,
Prashant.
sir.
Pace is fine, sir.
Pace is fine. All right. Okay, so I will try to maintain this pace. It will become a little faster as we go along, because then you will also try to pick up things easily. But anyway, so any other question? Yeah,
Sir.
for 3 more. Yeah.
Sir, why you take delta t is less than 1? Because delta t tends to 0 is more appropriate for answer.
Right. You are right. But so now see, how will you represent delta t tends to 0 when you are writing delta t in terms of numbers? See, numerical, I will write everything in terms of numbers, right?
Yes, sir.
So how will I write delta t tends to 0? What will be the value of delta t in that case? It cannot be 0. That's not tends to 0. And if it is 0, obviously I cannot define the difference, the d theta dt, because it will blow up.
Yes, sir.
So then how do I represent delta t tends to 0?
Okay. So sir, delta t is less than 1. So how define delta t
So
value?
you can ask the question that how small should I take the value of delta t, right? So that's
Yes,
a valid question. So that question we'll see next time. So see, the question you are asking is, if I take delta t equals to 0.001, how much error do I make in my computation, right? So I will get a value of theta which is not so accurate, right? But how much inaccuracy will creep in if I take delta t to be 0.001 compared to say 0.1?
Yes,
So
sir.
it is kind of obvious that 0.001 is will be more accurate in this case. But so that will depend on how accurately you want to know the result. So we need to have a way of transforming these approximations to how much error we are making into the calculation, right? So the next thing that we'll learn is what are the different types of error that we make in numerical computation. And you will also see that much of those errors doesn't come because we use a computer. Like for example, this error, delta t 0.001, as I said, I will take. this error will be there even if I am calculating by hand, because I have to say delta t to be a finite but small number. So it's not a problem with of a computer, but then there will be errors which are coming because of the modern day computers. You're not doing it by hand, or you don't have infinite time to do the computation. Okay, so there are different types of errors that one encounters when do computation. So that is what we'll learn next time. And it's very important to know that what is the scope of the techniques that you are learning. So you say, I learned some technique and I try to apply it everywhere. Like, for example, you learn to ball a bouncer and you try to apply it to Firoz Shah Kotla, which is a cricket ground at Delhi, and the ball will not bounce past the chest. So every bouncer that will ball will be pulled down to the mid-wicket boundary. Okay, so you need to learn where you should apply and what are the limitations. So that is the first thing that we'll do next class. Any other question?
Sir, what is the numerical notification of delta t is less than 1?
There's no numerical notification, numerical notation for that.
Sorry, sir.
Why do you need a numerical notation?
Yes, sir.
Who was recording? Are you still there? Who are you? Karthik, okay. So Karthik, if you record the other classes also in case I forgot, then it will be good. That is okay. If you share with me, all of them I can join them and keep it. That is all right. Next day, one of you remind me of starting the recording at the beginning. Okay. Okay. So I think that's it for today. I will be here for next 5 minutes if you want to ask anything. Otherwise, if you want to leave, you leave.
Sir?
Yeah.
Sir, in this exercise that you have given, we have to take delta t same for like all the combinations.
Yeah, you take delta t same for all the combinations.
Okay. So can we take 0.001?
Yeah. So whatever is written, 0.001 is fine. All right. Let's call it a day. We'll see you in the next class.